We are in section 7.5, Strategies for Integration. This section summarizes what we've learned over the past few sections in this course, and then also what we've discussed in Calculus 1 with integration techniques. And so first thing says, know the table of integration formulas on page 503. Something to look at and make a reference for. You have also received a handout from me with different formulas on it. First thing here says integration 4-step strategies. This is on page 504 and 505 in our textbook. The first thing is to simplify the integrand if possible. Maybe it's with rewriting trig expressions, or maybe factoring, or maybe reducing out a fraction, but some way to simplify it. 2 says look for obvious substitutions. This would be using U-sub, a method that we've discussed in Calc 1 and also in Calc 2. And then 3 is going to be to classify the integrand according to the form. It's either a trigonometric function, a rational function, integration by parts, or radicals. And then the other thing to note, the biggest one here, is that if it doesn't work, that's okay, it happens. You're just going to erase it and try it again using another method. The first example here says evaluate the integral of sine cubed x over cosine x dx. And so I note that there's quite a few signs up in the numerator, so I'm going to go ahead and pull out 2 of those signs and rewrite this as sine squared x times sine x all over cosine of x dx. And then using the Pythagorean identity, I'm going to rewrite this sine squared x as 1 minus cosine squared x times sine x all over cosine of x dx. From here, I'm going to let u equal cosine of x, and then our derivative is going to be negative sine of x dx. I'm going to do the correct substitution for this problem, and I have a negative, I'll put that out in front. The integral of, and it's going to become 1 minus u squared over u du. I can separate this, the numerator over the denominator, so I would have 1 over u minus u squared over u, or just u du. From here, I can easily integrate this. I can also deal with the negative now or later. I will just leave it out in front, but you can definitely distribute it through. So I'm going to have negative, the integral of 1 over u du is going to be our natural log of the absolute value of u. And then I have minus 1/2 u squared. Since it's an indefinite integral, I'm going to put my plus c. I'm going to go ahead and distribute that negative through now, and also substitute back in what u is. Remember, u is equal to cosine of x. So I'm going to have negative natural log of the absolute value of cosine of x plus 1/2 cosine squared x plus c. And this would be my final answer here. There's another example right below this. It's a definite integral. This one says evaluate the integral from 0 to 1 of 3x plus 1 to the square root of 2 dx. So first thing I note, and I want you guys to note, is that yes, the exponent looks a little different, but it's just a numerical value. So this is just like what we would have before, where it was a value raised to an exponent, like to the 4th or to the 5th. And since it's not just a variable raised to it, it's a function, it's 3x plus 1. I know that we dealt with those by using u-sub, so I'm going to let u equal 3x plus 1. That means that du is equal to 3 dx. So our integral, and since it is a definite integral and we are using u substitution and changing this variable, I know that I need to change those limits of integration, and I'll do that momentarily. But for the first part, we have u to the square root of 2, and then it's going to be 1/3 du, and I'm going to put the 1/3 out in front. And then my limits of integration, so the upper limit is now going to be 3 times 1 plus 1, so it's going to be 4. And my lower limit of integration is going to be 3 times 0 plus 1 which is 1. From here, you can integrate. This is just using the power rule. Remember, you add 1 to the exponent since it's just a number and divide by that same value. So I do have the 1/3 times, and it's now going to become u to the square root of 2 plus 1. And I'm going to multiply by the reciprocal of that value or divide by it, which is 1 over rad 2 plus 1. And from here, I can evaluate this from u equals 1 to 4. So from here, I'm going to have the 1 over 3 times the square root of 2 plus 1. You can distribute that through if you would like. And then it's 4 to the square root of 2 plus 1 minus, and then 1 to any power is still 1. So we'll just say times 1. So this is my final answer. The example at the top of the next page, I'm going to go ahead and circle, and we'll work on that one together in class. The next example says evaluate the integral of x over x to the 4th plus x squared plus 1 dx. For this example, it reminds me of partial fractions possible, but it needs to have completing the square done. I also noticed that it's x to the 4th and x squared, and I'm going to go ahead and see about simplifying this a little bit with this substitution. So I'm going to let u equal x squared, and that means that du would be 2x dx. And so this integral is now going to become 1/2, which I'll put in front, 1 over, and since x to the 4th is x squared squared, this is going to become u squared plus u plus 1 du. From here, it's still, I'm not able to factor it. That would be nice if I could. And so I'm going to go ahead and try to complete the square. And so completing the square, and I'll go ahead and do that over here on this side, I need to add and subtract something. So to complete the square, we're going to add and subtract b over 2 squared. And so right now I have u squared plus u, and I'm going to add in something, and then I also have a plus 1, and then I'm going to subtract that same something that we have. And so the something that goes in there is b, which in this case is 1 over 2 squared. So we're going to add it and subtract it, and that way it's like we didn't do anything to the problem. From here, this left side is going to become u plus 1/2 quantity squared, and then I have a plus 1 minus 1/4, which is going to become plus 3/4. And so I'm able to rewrite this as 1/2 times the integral of 1 over, and it's u plus 1/2 squared plus 3/4 du. So from here, it looks like something where maybe I could use tangent inverse possibly, but I'm going to go ahead and do another substitution and just say let's let v equal u plus 1/2. Then dv is equal to du. So this is now going to become 1/2 the integral of 1 over v squared plus 3/4 dv. And let's make a little note here. So I want you guys to remember one of the formulas that you should have memorized now, but if you don't, definitely make some flashcards. 1 over x squared plus a squared dx, the integral of that, is going to be equal to 1 over a times tangent inverse of x over a plus c. So it looks very similar. So if I rewrite this as the integral of 1 over v squared plus, and this would be rad 3 over 2 all squared dv. It looks like the integral of this would be a tangent inverse. A for this problem is going to be rad 3 over 2. So integrating this, we're going to get 1/2 times, and it's 1 over a, so 1 over rad 3 over 2, tangent inverse of, and it's x over a. For x, we have v, and a is rad 3 over 2 plus c. Simplifying this, we have 1/2 times, it's going to become 2 over the square root of 3, tangent inverse of 2v over rad 3 plus c. Our 2's are going to reduce out, and now we have to start back subbing. So we know that v is equal to u plus 1/2. So we have 1 over the square root of 3 tangent inverse of 2 times v, and v is u plus 1/2, all over rad 3 plus c. I'm going to distribute my 2 through, that way it kind of simplifies this a little bit. And so I have 1 over the square root of 3 tangent inverse of, and it's going to become 2u plus 1, all over rad 3 plus c. And now I still need to back sub in what u is, and u is back up here. U is equal to x squared. That way we get back to our original variable. So we have 1 over rad 3 tangent inverse of 2x squared plus 1 all over rad 3 plus c. And this will be our final answer. The next example says to evaluate the integral from 0 to rad 2 over 2 of x squared over the square root of 1 minus x squared dx. So this one looks similar to maybe like a trig substitution problem. And so I'm going to think about if I were to sketch a triangle. Put theta on here, it's a right triangle. The hypotenuse would be 1, and my opposite side would be x. Adjacent side would be 1 minus x squared. And so we know that sine of theta is equal to x over 1, which means we're going to let x equal 1 times sine theta, or just sine theta. Then we see that dx is equal to cosine theta d theta. And so the square root part that we have, which is 1 minus x squared, and then subbing in what we have for x, which is sine theta. And so this is 1 minus sine squared theta, or cosine squared theta. And the square root of cosine squared theta is just cosine of theta. And so now our integral, which was from 0 to rad 2 over 2 of x squared over the square root of 1 minus x squared dx, is going to become, and x again is sine, so we have sine of theta squared over, and then the square root of 1 minus x squared, we arrived at cosine of theta. And then dx we have as cosine of theta d theta. And since I now have an integral with the terms of theta, I need to change my limits of integration. I don't have much room up here, so I'll kind of draw them over here. So subbing in my upper limit of integration, that's an x value, so I'm going to have rad 2 over 2 equals sine of theta. And sine of theta equals rad 2 over 2 when theta is equal to pi over 4. So my new upper limit of integration is going to become pi over 4. Likewise, my lower limit of integration was 0, so x was equal to 0. And sine of theta equals 0 when theta is 0. So theta is going to equal 0. So my lower limit of integration is 0. From here, you can reduce out those cosines of thetas, and then sine squared theta, we can use our power reducing formulas. And that is 1/2 times 1 minus cosine of 2 theta d theta, just using those formulas. And I have a 1/2, and then integrating this, since I'm integrating with respect to theta, this will become theta minus, and then it's 1/2 sine 2 theta. And we are evaluating this from theta equals 0 to pi over 4. So substituting in pi over 4 first, we have 1/2 times pi over 4 minus 1/2 sine of, and it's 2 times pi over 4, or 1/2, minus, and then subbing in our lower limit of integration, I have 0 minus 1/2 sine of 2 times 0, which is 0, and sine of 0 we know is just going to be 0, so we'll put that in next. So from here, we have 1/2 times pi over 4 minus 1/2 times, and sine of pi over 2 is just equal to 1. And we know that this is just going to become 1/2 times 0 minus 0, so this whole term just will be 0. You can distribute the 1/2 and simplify that a little bit, but we get pi over 8 minus 1/4. The next example we have says evaluate sine of radical at dt. And in this problem, a is just a constant. And so I'm going to go ahead and see if I can just rewrite this in terms of like sine of x or sine of theta. So I'm going to let x equal the square root of at, just to kind of see if I can simplify this somehow. That means that x squared is equal to at, since I squared both sides. And I can differentiate the x equals the square root of at, or I can differentiate both sides, x squared equals at. And I'm going to differentiate that one just because it's a little bit easier and a little bit cleaner to deal with. So this is going to be 2x dx equals, and the derivative of at with respect to t is just going to become a dt. And so from here, I know that dt is equal to 2x over a dx. So the integral that we have originally, which is sine of square root of at dt, if I use this substitution, this is now going to become the integral of sine of x times, and then dt is the same thing as 2x over a dx. And so kind of rewriting this, I'm going to pull 2 over a in front of my integral since that is just a constant. And then I have x times sine x dx. And so for this problem, I have two parts. I have a trig part and I have a polynomial part, so I'm going to try integrating by parts. Doing that, I'm going to let u equal x, and dv is going to equal sine x dx. So differentiating both sides for the first part, I get du equals dx, and then integrating both sides, I get v is equal to negative cosine of x. So using our integration by parts, my integral is now going to become, and I have a 2 over a out in front, and then it's u times v, so it's x times negative cosine of x, I'll put the negative out in front, minus the integral of v du, and so it's negative cosine of x, again I'm going to pull that negative out and make that positive, and then dx. So from here I can integrate this, and so I still have that 2a, 2 over a, negative x cosine of x, still the same. And then integrating cosine of x dx, we get plus sine of x. And since I'm done integrating, I'm going to put a plus c. From here, I need to back sub in what x is, and x is equal to the square root of at. And so this is going to be 2 over a times negative square root of at cosine of square root of at plus sine of square root of at plus c. The example on the next page says evaluate the integral from pi over 6 to pi over 3 of sine x cotangent x over secant of x dx. So for this problem, I have a lot of different trig functions, and so I'm going to first rewrite everything in terms of sines and cosines, and hopefully simplifies enough to be able to integrate this. And so rewriting this, I'm going to have the integral. It's still going to stay from pi over 6 to pi over 3 of sine x times cotangent, which is going to be cosine of x, over sine x, all over secant, which is 1 over cosine of x dx. So I need to simplify from here. I notice that my sines are going to reduce out, which is nice. And then if I multiply both top and bottom by cosine of x, this is now going to become the integral from pi over 6 to pi over 3 of, and then I'm going to have cosine x times cosine x, or cosine squared x dx. And anytime we have cosine squared or tangent squared or sine squared, I'm going to use those power reducing formulas that we do need to know. And so this is still going to stay the integral from pi over 6 to pi over 3. And we're going to have a 1/2, and this one is 1 minus cosine of 2 theta. And in this problem, it's going to be x dx equals, and so from here we can integrate this, and so I have a 1/2 out in front, and then I have x minus 1/2 sine of 2x, and we're evaluating this from pi over 6 to pi over 3. So I'm going to substitute in my upper limit, and so I have x is pi over 3 minus 1/2 times sine of 2 pi over 3 minus 1/2 times substituting my lower limit, which is pi over 6, minus 1/2 sine of 2 times pi over 6. This is just going to simplify to pi over 3. So I have 1/2 times pi over 3 minus 1/2 times, and then sine of 2 pi over 3 is going to be rad 3 over 2 minus 1/2 of pi over 6 minus 1/2 times, and then sine of pi over 3 is rad 3 over 2. And distributing through my 1/2 and simplifying this, we end up with pi over 6 minus rad 3 over 8 minus pi over 12 plus rad 3 over 8. And so your rad 3 over 8s will reduce out, and then we're left over with pi over 6 minus pi over 12, which is just going to become pi over 12. The next example we're going to circle, and we'll work on that one together in class. The next example says evaluate the integral of 2x minus 3 over x cubed plus 3x dx. So this one reminds me of partial fractions. And so if I did that, I'm going to rewrite this as 2x minus 3 over, and I can factor out an x. And really quick, I can't use long division because the numerator, the degree in the numerator is smaller than the degree in the denominator. And again, that long division works when it's the flip, when the numerator is larger than the degree in the denominator. So from here, I notice that I have x squared plus 3, which is a quadratic factor that doesn't reduce anymore. And then I also have x, which is a linear factor, which doesn't reduce anymore. And so using partial fractions, this is going to become the integral of a over x plus, and then over the other factor, which is x squared plus 3, since this is a quadratic factor, I'm going to have bx plus c dx. And so I know that the two integrands are equal. So it's equal to a over x plus bx plus c over x squared plus 3. And I am going to multiply both sides by that common denominator, which is x times x squared plus 3, which is going to become 2x minus 3 equals a times x squared plus 3 plus bx plus c times x. And we talked about different ways to handle these problems. And so I'm going to go ahead and let x equal 0, because that would cancel out that last term that we have on the far right of my equation. So I'm going to let x equal 0. And when we do, we'd have 2 times 0 minus 3, or negative 3, equals a times 0 squared plus 3, which is just 3, plus 0. And so from here we get that a is equal to negative 1. I'm going to underline it so I can keep track of that. So now I need to determine also b and c. And so looking at this, I notice that I have a times x squared, and then I'll also have bx times x, which is also an x squared. On the left side I have no x squared, so I'm going to go ahead and put 0x squared equals, and it's going to be ax squared plus bx squared. Just looking at those x squared terms, remember this is an equation, so those x squared terms have to equal each other. So this is the same as saying 0 equals a plus b, and we know that a is equal to negative 1, so b is equal to positive 1. Now we need to determine c, and it looks like c has an x with it, and that's it. So I noticed on the left side I have 2x equals, and on the right side the only term that has an x would be cx. Dividing both sides by x, we get 2 is equal to c. So from here, our integral is now going to become the integral of, and we have negative 1 over x plus, and then we have bx, which is just going to be 1x, or just x, plus c, so plus 2, over x squared plus 3 dx. And so integrating the first one, that is negative ln of the absolute value of x. And then for the second one, what we're going to do for that second term, I'm going to split this. I'm going to say this is the integral of x over x squared plus 3 dx plus the integral of 2 over x squared plus 3 dx. And this last term that we have, this is actually going to be tangent inverse if you look back at your formulas for that, if you don't know it yet. And for this middle one here, I'm going to go ahead and look at this one first. And this one I'm going to let u equal x squared plus 3, and du is equal to 2x dx. And so this integral, and I'm going to bring the other ones down in a moment, is going to become the integral of 1/2 times 1 over u du. And 1 over u du is going to be ln of the absolute value of u. So this is 1/2 ln of the absolute value of u, which is going to become 1/2 ln of the absolute value of x squared plus 3. And then the far right term is going to be my tangent inverse. So I'm going to put this all together. So the first term we had was the ln, negative ln of the absolute value of x. My second term, when I integrated, was 1/2 the natural log of x squared plus 3. And then the third term that we have is going to be the integral of 2 over x cubed plus 3, which is going to become plus 2 times, and using our tangent inverse, 1 over rad 3, since that's a squared would be rad 3 squared, so 1 over a tangent inverse of x over rad 3 plus c, since we're done integrating. And this would be our final answer. You can definitely put the 2 over the square root of 3 if you wanted to, just to make it look a little bit cleaner. But this would be our final answer.